Okay, so a type of EM radiation has a wavelength of 55.1 nanometers. What is the frequency of radiation in hertz, or in other words, inverted seconds? Both of those mean the same thing. So we're going to be using this equation. The speed of light is equal to the wavelength times the frequency. And speed of light is 3.00 times 10 to the 8 meters per second, which means that our wavelength has to be in terms of meters if we're going to put it in there, because we have meters per second up here. We need this to be in meters. So what I do is I take 55.1 times 10 to the minus 9 meters. And since we can move the decimal place over, you can put 5.51 times 10 to the minus 8. Since normally we'd want it in this form, but since this is just getting us along the way to the final calculation, you can put it directly into the expression this way. I'm not going to mind that at all. But we have nu is equal to c over lambda. So check with your instructor if I'm not your instructor, but I wouldn't mind that because it's just that's not going to be the final form. So, but you do definitely have to change from nanometers to meters. So meters cancel, and you see we're left with inverted seconds, which is units of frequency. And we end up with 5.44 times 10 to the 15th. It should be a very large number. Inverted seconds, which is also can be written as that many hertz. Okay, now a type of EM radiation has a frequency of 3.33 times 10 to the 15th. Sorry, it's when we have that kind of number, it's minus because it's usually small. But here, frequency is going to be a very large number. So if you do see 10 to the minus 15 hertz, stop and look at it because that's really wild. There's really no limit on frequency or wavelength, but if you have a frequency that's 10 to the minus 15th, you gotta, that is highly unusual. It's unlikely that that anyone has measured that kind of frequency because it'd be so slow. But there's no theoretical limit, but we should expect normally that you stick with things that you're going to see in the real world. Okay, so here's our frequency, our wavelength. It then is going to be c over frequency. So c, let me rewrite it. And then we have 3.00 times 10 to the 8th meters per second. You might say, are you sure you're in the right units? Well, let's check. Because we want wavelength, and that's going to be in meters. Now this is per seconds, or inverted seconds. This is inverted seconds on the bottom. So we end up with meters, so yeah, we are in the proper units. But if it had turned out to be something, they weren't in the proper units, you'd have to make that change over. In this case it worked out. This is 9.01 times 10 to the minus 8 meters. Now they want it in nanometers. So looking at this, I know that it's 90.1 nanometers. But if you aren't sure, that's okay. No big deal. I've done this for a while, so I know what I'm looking for. But you just take this, divide by 1 meter is 10 to the 9th nanometers, and then work it out. And you end up with 90.1 nanometers. So be careful, whatever is being asked for. It's one thing to get the answer in meters, but maybe that's not what they're asking for. Maybe it's in nanometers. If it is a longer wavelength, they might want it in kilometers. That'd be unusual, but they might want it in some other units. So kilometers would be unusual, but something like microns or micrometers or what would be the next one up? So millimeters, that's a possibility as well. So just make sure you're in the right units. Okay. And then, so we have this arranged in the order. Okay, so we want to arrange these types of EM radiation according to wavelength, increasing frequency, and increasing energy. So for my class, I just give you the EM spectrum, and we find that we have gamma rays are the highest in energy, and how we have it set up. Let me just put it in order first. So increasing wavelength. Gamma rays are the highest energy, which means they have the smallest wavelength. So they're going to have the smaller wavelength than X-rays, and this will be read right out of the table. Then we have far IR, and if you have your table handy, just check and you'll see what I'm doing here. And the radio waves have the longest wavelengths of them all, on the order of meters, even several meters in length. Gamma rays can get down to, you're talking about 10 to the minus 20, 10 to the minus 18 meters down here in this range. Very, very, very tiny. It can be extremely small. But then if we talk about increasing frequency, that works in the opposite way. As the wavelength goes up, the frequency goes down, and vice versa. So as the increase in frequency, that would work exactly the opposite way. Radio waves would have the lowest frequency. Radar would be the next. Far IR. And these are just some of them that are in the table. If you check your table out in your book, you'll see there's lots of others, but I just picked these. Gamma rays. And then increasing energy. This is jumping ahead to the next lecture, but energy is equal to h nu. This is frequency, this is energy. So we can see that energy is proportional to frequency. So as the frequency goes up, the energy goes up. So we don't even have to rewrite it for increasing energy. They both move in the same way, but the wavelength moves in the opposite way. As you increase the wavelength, the frequency decreases and the energy decreases. So the highest energy photons are going to be ones that have the highest frequency or the shortest wavelength.